All right, so this is Precalculus, Chapter 4, Section 1, called Polynomial Functions and Models. It's really disappointing because you think it's going to be like pretty skinny girls with fluffy hair, but not that kind of models. It's mathematical models, so fortunately. Or really washboard ab dudes with the squinty eyes that look off into the distance. Not that kind of model. But even better because they're polynomials. Okay, so my favorite part of math is identifying because there's no math involved in identifying. So identifying polynomial functions and their degree, mega easy because so a polynomial function looks like this, and I could rattle it off to you. It's f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1, where the sub, these guys just tell you it's a different coefficient here than it is here. Coefficients are real numbers, and n is a non-negative integer. So your exponent, in order to be a polynomial, your exponent has to be non-negative and an integer, like a real number. So the domain is the set of all real numbers. So a polynomial, there's no restriction on what you can input into a polynomial for your x value. Kind of like when you have square roots, you can't put in negatives. When you have denominator, you can't make it 0. There is none of that shiftiness in a polynomial. Pretty straightforward. They'll always treat you right, those polynomials. All right, so identifying polynomials, let's look at this first one here. If we have f of x equals 3x minus 4x to the third plus x to the 8th, all the exponents on your variable are positive, and they are whole numbers. So it is a polynomial, and it has a degree of 8. So you find the highest degree exponent stuck to your variable, and that's the degree of your polynomial. B, checking it out, not a polynomial because of the denominator having the variable in the denominator. H of x equals 5. It is a polynomial. The degree is 0 because x to the 0 is 1. 1 times 5 is 5. So if we have a 0 as an exponent, that is okay. F of x equals x minus 3 times x plus 2. What's our guess? Yes or no? Just shout it out. There. It is a polynomial. It's degree 2 because when you FOIL it out, so to find degrees of polynomials, we've got to FOIL out and get the highest exponent on our variable. So it's a second degree polynomial. Look at this guy, g of x equals 3x minus 4x to the negative 1. Is this a polynomial? Thumbs up if it is, thumbs down if it's not. It's okay, I'm not grading you on your answer. It is not because the integer needs to be non-negative. So your exponents need to be non-negative. And in fact, if you look at, you compare it to b, it's pretty similar to b because a negative exponent just means fraction. So it would be the same as 4 over x. And we know that that's not a function. Okay, let's look at f, last one. 1/2 x cubed minus 2/3 x squared plus 1/4 x. Thumbs up or thumbs down? Consensus is thumbs up. It is a polynomial. It's degree 3. See, no math involved, just identifying. I love it. Quick and easy. Make sure if it's asking you to give an explanation, you guys include that. explanation. All right, so here's the summary. F of x is equal to 0. It's called the 0 function. It's the x-axis on a graph, and it has no degree. 0 degree is just a constant, just one single number, as long as it's not 0, because then it would be a 0 function. It is a constant function. It is a horizontal line with y-intercept at whatever value you're equaling your function to. First degree looks like this. We have a coefficient times x plus some value, and as long as your coefficient multiplying by the x isn't 1, that gives you a linear function. We've seen them. This is kind of like y equals mx plus b, same kind of form. It's non-vertical, non-horizontal. Slope is our coefficient, and y-intercept is whatever we're adding to the end of it. Second degree polynomial kind of looks like this. a2x squared plus a1x plus a0. As long as your first coefficient is not 0, it's a quadratic. We dealt with quadratics the last couple chapters. The graph is called a parabola, and it's smiley face if your coefficient is greater than 0, and it's frowny face if your coefficient is less than 0. All right. If you're a polynomial, because your domain is all real numbers, there's no holes, no gaps, no weird corners. It's nice and smooth and continuous. If you're not a polynomial, look how wonky you get. You could have a corner. This is called a cusp. You could have a gap or a hole. So the difference in graphs between polynomial and not polynomial: smooth and continuous, and then wonky, not a polynomial. Power functions. A power function of degree n is a function of the form f of x equals axn, where a is a real number, n is greater than 0, and is an integer. Let's see how some of these look. First degree looks like this. Second degree, second exponent. Third degree, exponent's cubed. Variable is cubed. Fourth degree, exponent is 4. Difficult there. All right. Even functions. Even functions are going to behave a lot like a parabola. An even function has values that, especially if the coefficient is positive, starts up and ends up. So if you look at the y equals x to the 4th, it starts up and ends up. So y equals x squared is more of, at the base it comes down, is a little bit pointier, and then to the 4th power it starts, or this is to the 8th power, starts kind of widening out as you get higher powered. But unless your exponent, or unless your constant in front of it is negative, or your coefficient is negative, then it'll start down and end down. So even functions start up, end up, or start down, end down. Very similar to parabola. All right, so we're going to graph some things in our graphing utility, which could be Desmos or your graphing calculator. When you graph y equals x to the 4th, y equals x to the 8th, and then y equals x to the 12th. The shape is similar, it just starts getting wider and wider at the base here. The base kind of flattens out. So if n is a positive even integer, f is an even function. So its graph has symmetry to the y-axis like a parabola. The domain is all real numbers, and the range is a set of non-negative real numbers. And that's especially if it's smiley face. The graph will always contain these points, -1, 1, 0, 0, and 1, 1. As the exponent n increases in magnitude, the function increases more rapidly. When x is less than -1 or x is greater than 1, but for x near the origin, the graph tends to flatten out and lie closer to the x-axis. We saw those on the pictures. All right. Odd functions. So when your exponent is odd, like x to the third and up, x to the fifth, x to the seventh, x to the ninth, you get a function that looks really close to our x to the third. It's our swimmer function. So you can tell if a function is odd by looking at it, if it resembles a swimmer. As we increase the degree, the graph between -1 and 1, it flattens out and hugs the x-axis a little bit more. So we compare them. We see that flattening out along the x-axis. But they all behave similarly. They all behave like an x to the third function. Okay, so when f of x equals x to the n, where n is a positive odd integer, the function is odd. So the symmetry is with respect to the origin. That's from last chapter. The domain and range, all real numbers. You can go all reals. So check this out. This is a little bit different from even functions. -1, -1 is on the graph, 0, 0, and 1, 1. As the exponent n increases in magnitude, the function increases more rapidly when you're less than -1 or you're greater than -1. But near the origin, the graph flattens out and hugs it. All right, graphing polynomial functions using transformations. Oh, I love transformations. So we're going to graph 1 minus x to the fifth. It's going to look like a swimmer because it's odd. And it's going to start negative, come through the origin, and end up when x is positive. So it's going to start up from, this would be x to the 5. This minus sign is going to switch, so it's going to come up. It's going to start in the y positive and come down. And then this 1, this positive 1, is going to move everything up 1. So swimmer function, reflected, and moved up 1. All right, so this function is going to be, it's 4th degree, so it's going to resemble a parabola. What's the 1/2 going to do to it? Yes, it's going to make it wider, and this -1 is going to move it. It's going to, you're right, no, I'm sorry. It does move it right 1. It's opposite. Okay, so here's our x to the 4th, looks like a parabola. We're going to move it to the right 1 unit. And we're going to flatten it by a factor of 1/2. All right, identifying the real zeros of a polynomial and their multiplicity. Your 0 is where you cross the x-axis. We've been doing that for a while. If f is a function and r is a real number for which f of r is equal to 0, then r is called a real 0 of f. As a consequence of this definition, that summons you. The following statements are equivalent. R is a real 0 of the polynomial f. R is an x-intercept. x minus r is a factor, and r is a solution to the equation f of x equals 0. So tons of stuff. If we find a real 0, it truncates all these items out of just that one fact. Okay, find a polynomial of degree 3 whose zeros are -4, -2, and 3. Use a graphing utility to verify your results. So if we go back to one thing we know for sure, we can say x minus r is a factor. So when we're putting together a polynomial as such, we say x minus -4, x minus -2, and x minus 3 are all part of our function. We don't know what our coefficient value out in the front is going to be, so we have to leave it as a. You multiply all those out and you get x to the third plus 3x squared minus 10x minus 24. If you would like me to do that for you, please let me know and I will do it later. We are going to choose a value of 1, and I recommend doing that as much as you can. If you get the choice, choose a equals 1. And when you graph it, you see it crosses the x-axis at -4, -2, and 3. You can make the coefficient -1, and it would just reverse this graph. All right. If you pick the coefficient of 2, it just lengthens your graph. It doubles the extension of your graph. So here, this graph only went up 1 here. It goes up 2 on this graph. And all 3 of these are viable answers to this. If x minus r to the m is a factor of the polynomial f, and x minus r to the m plus 1 is not a factor of f, then r is called a 0 of multiplicity m of f. A 0 of multiplicity m of f. Okay, that's mathy talk, so let's see what that really looks like. For the polynomial, list all the zeros and their multiplicities. So you see how sometimes if we have a higher power than 1, it indicates a multiplicity. 2 is a 0 of multiplicity 2 because the exponent on the factor of x minus 2 is 1. -1 is a 0 of multiplicity 3 because the exponent on the factor of x minus 1 is 3. I think this is wrong. I think this needs to be 1. Because what is the exponent here? 1. I think they made a typo. 1. Okay. Let's proceed.
Yeah, that makes more sense.
Yeah, you're
Then 1.
right. Let's try this again. 2 is a 0 of multiplicity 1 because the exponent on the factor is 1. Okay. -1 is a 0 of multiplicity 3 because the exponent is 3. 3 is a 0 of multiplicity 4 because the exponent on the factor is 4. So the multiplicity is directly based on the exponent. So for a polynomial, f of x equals x times x minus 3 squared, we're going to find the x and y intercepts. Use the x-intercepts to find the interval on which the graph of f is above the x-axis and the interval on which the graph is below the x-axis, and locate other points on the graph and connect all the points plotted with a smooth, continuous curve, because it is a polynomial. All right, so x-intercepts is where y is equal to 0. And you divvy this up when you're setting it equal to 0. You set it up where you have x is equal to 0 and where x minus 3 squared is equal to 0, and then you solve it out. So the x-intercepts are x equals 0 and x equals 3. The y-intercept is what you get when x is equal to 0, so you put in 0 for your x's, and we get out lovely 0. So the y-intercept is at 0. All right, so we're going to look at intervals. We're going to look at what happens between negative infinity and 0, which is our first x-intercept. Look at what happens between 0 and 3, which is our second intercept. And then look what happens between 3 and infinity. So when I plug in negative 1, I get out negative 16. It is below the x-axis. When I plug in 1, I get out 4 above the x-axis. When I plug in 4, I get 4 above the x-axis. So when you're putting that together on a graphing utility, it looks like this. So here is my intercept, intercept, intercept. We come up from below the x-axis, hit the origin, come up to 4, 1, 4, come down, and because I'm not below the x-axis in between here, I tap 3. So I tap it at 3. That's what multiplicity usually does. It causes a tap instead of a cross. I don't cross the x-axis, I just tap it at 3 and I go back up. So that's how you can have a 0 and still be above the x-axis. It just hits it. If r is a 0 of even multiplicity, the sign of f of x does not change from one side to the other. The graph touches. That's what we just saw. Just touches it. Just says hello and goodbye. If r is a 0 of odd multiplicity, then it crosses. So if it's a second power, it'll tap. If it's a third power, it'll go ahead and cross. Just kind of like a swimmer versus a parabola. So in this case, I have x squared. So at 0, so where this is equal to 0, I'm going to have something that is kind of a parabola shape. It's going to tap at 0 and move on. So x minus 1 is an odd. It's to the power 1. So at 2, I'm going to go ahead and cross. Versus here, I got y equals negative 2x squared. It is going to go ahead and tap at 0 and come on back down. So how we act near 0. So they're trying to point out that because x minus 2, and I'm ignoring the x squared right now, is kind of like a linear function, it's going to look a little bit linear at that point, right by 0. The multiplicity of a real 0 determines whether the graph crosses or touches at the x-axis. The behavior of the graph near a real 0 determines how the graph touches or crosses the x-axis. So this behaves like negative 2x squared near x equals 0. This behaves like 4x minus 2 near x equals 2. Turning points. So the turning point of a polynomial function of degree n has at most n minus 1 turning points. If the graph of a polynomial function f has n minus 1 turning points, the degree of f is at least n. That's really mathy talk, so let's see what that looks like. Okay. Which of the graphs in figure 16 could be the graph of a polynomial function? For those that could, list the zeros and state the least degree the polynomial can have. For those that could not, say why not. So we'll look at figure A. This graph cannot be a polynomial. It's got holes. It's got a gap. It's terrible. Polynomial can't have a hole or a gap. Okay, let's look at figure B. Figure B looks continuous. Looks like a polynomial. What degree do we think it is? At least third, because it's got 3 roots. 1, 2, 3. At least third degree.
So is that going to what degree it is by how many roots that has?
Definitely. And then you do a turning point. So you come here, it turns here, turns here, and goes down. Since graph has 2 turning points, the degree of the polynomial must be at least 3. So you take how many turning points you have, which here's a turning point, here's a turning point. So this has 2 turning points, so you add 1 to that to tell you that you must have at least 3 roots. So you can go either way. You can do it based on turning points, or you can do it based on roots. And you should probably look at both.
So something in degree of 8 would have 8 different roots.
Mm-hmm. Or multiplicity in combination with the roots. We have to kind of keep an eyeball on that, because the multiplicity will make it a little bit funny. This guy, function or no function? No function. He's got a corner. That's not a cusp. So, function or no function? Function. And let's see. Let's do it based on turning points and not roots. So we have 1, 2, 3 turning points. So how many roots? 4. So it could be a graph of a polynomial function has 2 real zeros at -2 and 1. Since the graph has 3 turning points, the degree of polynomial is at least 4. Because we could have a multiplicity of 2 and then 2 roots. Boop. End behavior. Oh, end behavior. For large values of x, either positive or negative, for a large absolute value of x, the graph of the polynomial resembles just the first term. So when you're looking at end behavior, you just look at your first term and completely ignore everything else. And that tells you what your function is going to behave like. For example, -2x to the third plus 5x squared plus x minus 4. The graph is a nice, this graph is a nice cubic function. Its end behavior is going to resemble -2x to the third. If it's an even function, then it's going to resemble as, it's going to go towards infinity as x gets more negative, and it's going to go towards positive infinity as x gets more positive. Unless your initial coefficient is negative, and then it's going to go faster and faster towards negative infinity as x gets more negative. More and more towards negative infinity as x gets more positive. So an even function will go more towards negative infinity on the negative side and more towards positive infinity on the positive side. An odd function will shoot down towards negative infinity as x gets more negative, or shoot up towards positive infinity as x gets more positive, unless your coefficient is negative, and then it's reversed. Identifying the graph. Which graphs could be the graph of x to the fourth plus 5x to the third plus 5x squared minus 5x minus 6? Which one of these could be this function? Which one can we exclude right away? We can exclude this one right away. Our coefficient is positive, so definitely we want up and up. We plug in 0 and we get -6. So we need a y-intercept at -6, so that excludes A. the degree is 4, so it can turn at most 3 times. So let's look. 1, 2, 3, 4. 1, 2, 3. That's 1, 2, 3. Definitely can't be that one. We already excluded that one, so it has to be B. Because it does turn 1, 2, 3 times. Oh, that was fun. All right. To summarize, graphing a polynomial, the degree of the polynomial is your highest exponent. The graph is smooth and continuous. Maximum number of turning points is your degree minus 1. Even multiplicity, it touches the x-axis. Odd multiplicity, it crosses. The end behavior is most like the first